Hello guys, so today we are talking QM, AM, GM, HM inequality. We're gonna be doing proofs, we're gonna be solving problems. You know, it's gonna be fun. Let's go. Okay guys, so first of all, what is the QM, AM, GM, HM inequality? Basically, this inequality states that there are few really interesting actually inequalities that happen to occur between means of certain non-negative numbers. So we have that for all non-negative xi's, maybe I will even write it down because I kind of didn't, xi's are in R plus. Lovely. I hope you can see this plus here better. So for all non-negative xi's, we have that the quadratic mean of n of m. Quadratic mean is just the sum of squares of those numbers divided by the quantity and square root taken of the whole expression, is greater than or equal to the arithmetic mean, which is just the most common mean to have ever existed, which is the sum of those n numbers divided by the quantity of them. And that arithmetic mean is supposedly, because we're going to prove it today, greater than or equal to the geometric mean of those n numbers, which is, well, just the nth root of their product, where n is the quantity of those numbers, and that geometric mean is greater than or equal to the harmonic mean, which is just the quantity of those numbers divided by the sum of the reciprocals. Lovely. So today what we're going to be doing is we're going to be proving first of all the AM-GM inequality, which occurs between the arithmetic and the geometric mean, as those acronyms kind of probably tell you. Those acronyms do probably tell you anyway. Yeah, and then we will be proving the GM-HM inequality, which, as you might have already guessed, is between the geometric and the harmonic mean. You kind of didn't really have to guess it because I told you just a few seconds ago. We're not gonna be proving the QM-AM inequality today though, and that's because well, this proof is kind of long and kind of hard. We will do it, but in a few future videos on inequalities like Holder's, Cauchy-Schwarz, stuff like this. So today we will be focusing mainly on AM, GM and GM, HM. We will also probably do maybe one problem or something about on the QM, AM inequality. We will be also covering some optimization stuff, and you know, as you can see, I'm excited, so let's just go on and solve some problems, guys. Okay guys, lovely. So we would like to prove the AM-GM inequality first, so that the arithmetic mean of some n non-negative numbers is greater than or equal to the nth root of the product, which is just the geometric mean. Lovely. So I would like to do it by induction. However, I'm not going to be using the regular induction, neither weak nor the strong version of it. I will be using the Cauchy induction, and if you don't know what Cauchy induction is, then I highly encourage you to check out my video on induction itself. That's probably the video just before the previous one. And so, just a quick reminder, the Cauchy induction, Cauchy induction works something like this. We first of all check the base case, which has to be n equal to 2. What we do then is we assume that the statement will hold for some k, assume for k, and then what we will do is not only prove that this assumption will imply that the statement will hold not for k plus 1 this time, but for 2 times k. That's proving all that's proving the statement for all powers of 2, but we will also prove using this assumption that the statement will hold for k minus a 1. This one looks like a new k minus 1. Why is it so? Here we're proving it for all the even numbers, and here, well, we're proving it for all odd numbers, and so summing it all up, we prove this statement for all natural numbers or all the integers. And so let's go on and do it. Let me clear the board because I will need a lot of space this time. So first of all, the base case. The base case is, by the definition, n equal to 2. And so for n equal to 2, well, we will get just two variables, yeah, arithmetic mean of some two variables, let me call them a and b maybe. So a and b over 2 is greater than or equal the square root, I'm not writing the square root base here, of the product. Lovely. So how do we do it? How are we supposed to prove it's true? Well, I will just square both sides. On this side I will get a squared plus b squared plus 2 times a times b all over 2 squared is 4, and on this hand side I will get just a times b. And so now, after multiplying both sides of the equation of the inequality by 4 and then subtracting 4 times ab from both sides of it, I will get the a squared plus ab squared minus 2 times the product is supposed to be greater or equal to 0, which, by the fact that the left hand side, this is my left hand, is actually equal to a minus a b squared, is always true for all real numbers a and b. Lovely. Yeah, beautiful. So the base case is achieved. What I would like to do now is assume that this inequality will hold for the value, I will actually write it down, assume will hold for n, yeah? And I would like to make the induction step of n implying, no, not n plus 1, man, I got used to that. N implies 2n, which is the first induction step, beautifully. So if I were to rewrite our statement in terms of 2 times n, I would get something like this. I will get x1, I'm adding stuff up to xn, then I'm adding xn plus 1, I mean sub n plus 1, and then I'm adding stuff again up to x sub 2 times n, and then I will divide everything by 2 multiplied by n, yeah? And I would like to prove that this is greater than or equal to the product of all those numbers to the power of 1 over 2 times n, but I'm not going to be writing the right hand side here. I will just be manipulating this expression here. So how can I rewrite it actually? Well, I can write it in a way that will be actually pretty nice, because I'm seeing here a nice way to use the base case and the assumption in order to prove the induction step. Why is it so? Because I can rewrite it as the arithmetic mean of the first n values, of the first n x's, then the arithmetic mean of the second part, yeah, second group of those n terms, so from n plus 1 up to 2 times n, and then everything by 2. Why is it nice? Okay, see it properly. Bear with me. Why is it nice? Because by the assumption we made earlier, yeah, and we assume that this is true for n, well, actually, it doesn't really matter what numbers we have here. Those can be, you know, x1 up to xn, they can be xn plus 1 up to x2 times n, it could be even x 2457 up to something n times more. That was a stupid analogy, wasn't it? Anyway, so we can say, by the assumption, this is actually greater than or equal to the nth root of the product of the first n terms plus the nth root of the product of x's from the n plus 1th one up to the 2 times nth one, I guess, and then everything divided by 2. However, now notice that those two are just some arbitrary numbers, yeah? And so what we can do here is recall that we actually proved the base case of n equal to 2, yeah? We proved by hand that for actually all all possible numbers in the domain of the problem, this is true, yeah, for like, you know, every single pair of those numbers, and this is just a pair of numbers, and so we can say by the base case, I'm going to write a nice arrow here so everybody knows that this is by the base case, we can say that it's actually greater or equal to the square root of the product of this first square root, not square but nth root, of the product of the first n, those n terms, and then the nth root of the product of numbers from x sub n plus 1 up to x sub 2 times n. And what is this equal to? Well, this is just the root to n of x1 times x2, and we are just multiplying stuff out, up to x sub n 2 times n, and this solves our problem halfly. I wanted to mark something like a half, yeah. Nice. 1/2, yeah. Because we still have to prove the statement for n minus 1. And I'll do it in just a quick moment, but let me firstly maybe like clear the board or something. Yeah. Okay guys, lovely. So the second part of the proof right here, I just clean up the board, though it's kind of messy still. Oh, who cares, guys? So we're supposed to prove that the statement holding for n implies statement holding for n minus 1. How are we going to do this? Well, first of all, acknowledge that our assumption is that this is true. You did it, you internalize it, lovely, we can move on with the proof. So I would like to make an assumption here, and some of you probably won't get why I can do this assumption, and I will elaborate on why I can do it in the videos to follow. However, this time I'm not gonna be elaborating on it because I'm not gonna be using this trick so much in this video. Lovely. So I would like to assume that the nth x is important, that the x sub n is going to be equal to the arithmetic mean of the first n minus 1 x's. Yeah. And why is this substitution absolutely awesome? My tongue is twisted as hell. Yeah. Why is it absolutely awesome? Notice one thing. If I substitute this substitution, that's something stupid. Anyway, if I substitute this xn into my original arithmetic mean of those n numbers, yeah, what I would get is x1, and I'm adding stuff up to xn minus 1, and then I have to add the arithmetic mean of the n minus 1 first x's, and then I will multiply everything by 1 over n, yeah, and divide everything by n. And after pumping my marker a little bit, because it's dying once again somewhere in the the US-Mexico border, whatever, I will get something like this. I will get that actually I can partition this fraction into two fractions, yeah? I can make myself one fraction, which is almost the arithmetic mean of those n minus 1 numbers, and then the second fraction is gonna be, well, this time the arithmetic mean of the n minus 1 first fraction itself, however, divided by n additionally. And what can I do now? Well, I would like to connect those fractions, because, well, I partitioned them, but I don't quite like having partitioned fractions, so maybe I was a bit of a hypocrite there, but I wasn't, bear with me. So I can bring those two to the common denominator to kind of make my life easier connecting those once again. And how do I do it? Well, I will just multiply and divide this fraction by the factor of n minus 1. I will multiply its nominator by n minus 1, and I will multiply its denominator by n minus 1. And what I will get by doing so, well, I will get something like this. I will get n minus 1, and then I will open a big parenthesis, huge parenthesis, and I will multiply it all by the sum from first x to the n minus 1 of x, and then I will divide all this stuff by n minus 1 times n, and then I have to still add this fraction to it. Yeah, and this is just the sum from x1 up to xn minus 1 divided by n minus 1 times n. But now there's one nice thing. Here we have n minus 1 times this sum. Here we have, well, absolutely the same sum, however, multiplied only one time. It is just one of those sums. Here we have n minus 1 of those sums. And so if we multiply together, if we add them up, not multiplying together, but if we add them up, what are we gonna get? We will get n of those sums, yeah? So we'll have n of those sums, but here we have an n in denominator. So those two n's will cancel each other out, and what we're gonna be left with is just the arithmetic mean of the first n minus 1 values. And why is it absolutely awesome, guys? Well, look at this. We know by our assumption we made earlier, yeah, that the arithmetic mean of any n non-negative real numbers divided by n, not the sum divided by n, the arithmetic mean is not supposed to be divided by n, it will be divided by n squared, so don't mind me, is always greater than or equal to the nth root of the product. But what's awesome here? Well, this is an arithmetic mean of n minus 1 real numbers. But what is it equal to? Well, it's equal to the arithmetic mean of n numbers, not n minus 1, n numbers. And so we can actually say that this stuff right here, which is equal to the arithmetic mean of n minus 1 things, will satisfy the assumption we made earlier. So, lovely, I guess, because now, let me erase all of this useless junk from the board. Yeah. Okay, lovely. So now what we can do is just, well, sub in this assumption we made for x sub n into this inequality, and what we're gonna get? Well, the left hand side, as we derived earlier here, will just become the arithmetic mean of the first n minus 1 numbers in the sequence xn. What about the right hand side? Well, I'm gonna have to make a little bit bigger square root here. We will just get same plain old product of the first n minus 1 numbers, however, multiplied by the nth number in the sequence. And what is gonna be the nth number in the sequence? Well, this is just the arithmetic mean. The arithmetic mean of the first n minus 1 numbers. Guys, this table is absolutely so awesome that I'm not gonna be recording this once again because of this little mistake, so yeah, bear with me. So, why is it nice? Because now I can just raise this inequality to, both sides of this inequality to the nth power, and what I'm gonna be left with? Well, the left hand side is gonna be just the arithmetic mean of those n minus 1 x's to the nth power, and the right hand side, absolutely, is gonna be equal to, well, the product of the first n minus 1 numbers multiplied by the arithmetic mean. But those two are the same. The only difference is that this one is risen to the nth power. You probably can see this n properly, can you? Yeah. This was awful. So what I can do now, well, I can just divide both sides of the equation by the arithmetic mean of the first n minus 1 numbers, and what I'm gonna be left with? Well, I'm gonna be just left with the arithmetic mean of the first n minus 1 numbers. Maybe this parenthesis was on the contrary a little bit too big. To the n minus 1th power greater than or equal to the product of the first n minus 1 terms. And now it's straightforward. You just have to take the n minus 1th root of both sides, and you have proven this statement for n minus 1. So we proved the statement for all even numbers and all odd numbers. Well, add it all up, we proved it for all natural numbers there are. And so AMGM is proven. Should have been n minus 1. Don't kill me. bye guys. No, not bye. It's literally the beginning of this video. We have like 8 more problems to go or something, so yeah. Not bye. Okay guys, lovely. So now I would like to prove the GMHM inequality, which states that the geometric mean of some n numbers, which is, well, just the nth root of the product, is greater or equal to the harmonic mean, which is just n divided by the sum of the reciprocals. Lovely. This time we're not going to be using any kind of induction. And why is this so? Because we've actually just proven the AMG inequality, which is gonna kind of straightforwardly imply this inequality, which you will see in just a few seconds. Lovely. So let's maybe do a quick recap in case you forget it about around like 30 seconds or something. I don't even have my watch here. That the AMG inequality states that if we have some n variables, let's call them x's, yeah, and we take the arithmetic mean, this is gonna be greater than or equal to the geometric mean, which is the nth root of the product. Okay, lovely. So you can see that this is kind of similar to the stuff we want to prove here. Here we have this, you know, like the sum of those x's over n, and here we have actually n over the sum of the reciprocal. So, well, those two look kind of similar. I mean, the reciprocal of this one would look kind of similar to this one, yeah? Yeah, just like how they wouldn't be the same. This would just look similar, yeah? And here we have the square root, which is also here. So maybe there's something to it. Maybe my intuition is not so all dusty and useless. Yeah. So let's try it out. So, you know, I'm thinking if we could make those xi's become 1 over xi's, you know what I'm talking about, then if we took the reciprocal of this hand side, we would just get the harmonic mean. Well, this makes quite a lot of sense. So let's define a new sequence, and I will call it AI, and I will say that AI is by definition equal. Well, those two dots just say that I'm defining it to become 1 over xi's, and you can clearly see now why I ruled out the 0 from here. Yeah, x's can be zeros. It would break math a little bit, just a little bit. Yeah. Lovely. And so now we can just go on and apply the AMG inequality for those AIs here. What are we going to get? Well, we will just get that the sum from the first A up to the nth A divided by n is greater than or equal to the nth root of the product of all AIs. Beautifully, but what are those? Well, this is just 1 over x1. We're adding this up to, well, just 1 over xn. And we're dividing everything by n. And what is it greater or equal to? Well, this is greater or equal to the square root, the nth root of 1 over x1, and we're multiplying stuff up to 1 over xn, yeah? But what can we do now? I can just go on and factor this 1 out, yeah? I mean, I can just say that this is actually equal to 1 over the square root, the nth root of the product of those n numbers. And so what I can do right now is I can just raise the inequality, I mean both sides of the inequality, to the -1 power, achieving something like this. I will just get that 1 over the sum of the reciprocals of x's is less than or equal to, well, this was the reciprocal, now we're taking the reciprocal of the reciprocal, so we'll just get the nth root, finally I didn't say square root, thank God, nth root of the product of all n's. And this, ladies and gentlemen, is exactly what we want to achieve, however, kind of mirrored, whatever, it's done. We can move on with our lives. We have a lot of problems left, so yeah, let's not waste any more time, guys. Okay, guys, so we're finally getting into solving problems in this video. So we're supposed to minimize x squared plus y squared under the constraint that the sum of x plus y is equal to 10. and that they are positive real numbers. And you're probably wondering why this problem is not in some kind of a calculus course, some kind of calculus lecture, but in a video on AMGM inequality. Well, bear with me, guys. So we know that x squared plus y squared is something that will kind of show up if we decide to expand this kind of a square, so x plus y expression squared. Yeah, we know that this is actually equal to x squared plus y squared plus 2 times x plus x times y. Yeah? And so this is kind of nice because we know what the value of this is. This is exactly 10 squared. This is just 100. And this is exactly what we're looking for. I mean, what we're looking to minimize. But what is this 2 times x times y? And now, you see, notice one thing. The AMGM inequality will state that the arithmetic mean of some numbers, some, whatever quantity of numbers you have, n numbers, is greater than or equal to the geometric mean. And so we can just, take two numbers, take the arithmetic mean, and so we just add them up and we divide it by 2. We divide the sum by 2, and this is going to be greater than or equal to the square root of the product. But now, what is this stuff? Well, this is just 10 by 2, so 10 by 2 is just 5, and so 5 is greater than or equal the square root of x times y. And so we're looking for 2 times x times y, so let's just, get those two to the second power and then multiply both sides of the equation by 2. What we're gonna get? Well, is just 50 is greater than or equal than 2 times x times y, yeah? And so we know for a fact that 100 minus 2 times xy is equal to x squared plus y squared. And we know that 2 times x times y is, its greatest value, yeah, is 50. Yeah? Every single time, all the way, is gonna be less than 50. And so this stuff is at least 100 minus 50, which is 50. So this is at least 50. And so we know that x squared plus y squared is also at least 50. And so this is our solution to the problem. That was fast. Was it? It was 3 minutes. It was awesome. Okay, guys, lovely. So we're moving further. Forward or further. Anyway, we are supposed to maximize the product of x times 1 minus an x cubed for x that between 0 and 1, and we're supposed to do it by AMGM inequality. But you see, the problem here is that with normally, sum that we would be given the value of, or a product would be given the value of, yeah. And so actually estimating up about using the AMGM inequality will be a little bit tricky here. However, there's a nice trick. You see. If we could find, for example, a sequence of some kind of terms, variables, numbers, whatever, that added together would be constant, yeah? So this like arithmetic mean of them would be a constant. Then, if also they satisfy the constraint that the product would be somehow linked to this expression right here, then, well, we could estimate the upper bound for the expression x times 1 minus x cubed using the AMGM inequality. And you see, I'm thinking, we have those x's here, we have those 1 minus x here, so maybe, adding some x's up together would give us some kind of a number, those ones. And so we're gonna do it. I would like to define ourselves a new constant, not a constant, a new variable y, that will be by definition equal to x times y minus x cubed. And why is it awesome? You see, now I can go on and just I can raise both sides of this equality to the power of 3. So y cubed will be equal to, well, x cubed times 1 minus x. 1 minus x, the x is cubed, and the whole expression cubed as well, beautifully. But now, you see, I can go on and multiply both sides of this equality by 3. And notice that this is actually equal to, well, 3 times x cubed times 1 minus x cubed times 1 minus x cubed times 1 minus x cubed. And so now, if I were to add those four numbers, here this is one number, this is the second number, third, and the fourth number. Now, if I were to add them up together, well, those 3x cubes would cancel out with those negative 3x cubes, and so I would just get 3. Lovely, because now I can use the AMG inequality. I can say that 3x cubed plus 1 minus x cubed plus 1 minus x cubed plus 1 minus x cubed all over 4, so the arithmetic mean of those numbers, is going to be greater than or equal to, well, the fourth root, but of what? Of the product, but the product is actually just 3y's cubed. Cubed, yeah? Lovely! So, what can we do now? Well, those x cubes will cancel each other out, so this will be just, well, 3/4. And we can just go on and multiply and raise both hand sides to the 4th power, and we will just get that 3 over 4 to the power of 4 is greater than or equal to 3 times y cubed. Yeah? And so, we see that 3 to the power of 3, actually, this will be 3 to the power of 3, but 4 to the power of 4 is greater than or equal to the y to the power of 3. And so this will mean that taking the cube root on both hand sides, we'll get that cube root of, well, 3 to the power of 3, 3 to the power of 3 over 4 to the power of 4 is going to be greater than or equal to x. So 1 minus x cubed. And this, ladies and gentlemen, is the upper bound for our expression. Okay guys, lovely. So the next problem here, however, before we begin, I need to specify one thing. So, as to the previous problem, move further typically means to move a greater distance or to a greater degree. It implies a sense of increasing or expanding. For example, I need to move further away from the fire to avoid getting burned. On the other hand, move forward typically means to make progress, to advance, or to continue. It implies a sense of moving towards a goal or objective. For example, we need to move forward with our plans to expand the business. And so we need to move forward with this problem to move forward with our video. Lovely. So we're supposed to prove that for all positive real numbers, ai's, such that the product is equal to 1, the product of 1 plus a1 times 1 plus a2 up to 1 plus an is greater than or equal to 2 to the power of n. And you probably could try it by induction or something like this. However, we're not gonna be doing this by induction. We will solve this one using the AMG inequality. And this is gonna be kind of straightforward. However, you kind of have to, well, notice one thing. So, first of all, notice that by AMGM, 1 plus a1, I mean the arithmetic mean, is going to be greater than or equal to the square root of a1. Yeah, lovely. And so what it implies? Well, it implies that 1 plus a1 is going to be greater than or equal to 2 times the square root of a1. Beautifully. But, by the same reasoning, 1 plus a2 is going to be greater than or equal to 2 times the square root of a2. And 1 plus a3 is going to be greater than or equal to 2 times the square root of a3. And we can go like this up to the an, so 1 plus an is going to be greater than or equal to 2 times the square root of an. And so right now, because there's absolutely no problem doing that, as all of those numbers are actually positive, we can just go on and multiply out. Yeah. I'm going to just multiply everything out together, and so what we will be left with is just, well, exactly the product we're trying to prove is greater than or equal to 2 to the power of n. And on the right hand side we'll just have, well, 2 to the power of n times the square root of, well, the product of those numbers, but what's the product of those numbers? Well, the product of those numbers is usually just 1. Lovely, and so this is just 1, so we can ignore it, and what we're left with is, well, literally what we're supposed to prove. So 1 plus a1 up to 1 plus an is greater than or equal to the power of n, which is the end of this problem. Okay guys, lovely. So I've been just singing Eminem for the past few minutes, and I'm finally ready to record one more problem. So we're supposed to prove that for two sequences, AIs and BIs, where BIs are just a permutation of AIs. What does it mean? Well, it means that those are the same numbers. It's gonna be crucial in this problem. They are the same numbers, but they are ordered differently. Yeah, so they are like put up in a line in a different order. Absolutely lovely. So we suppose that the sum of those kinds of fractions, so a1 over b1 up to an over bn, is greater than or equal to n for all values of n. Beautifully. So how can we do it? Well, I would like to actually I would opt for the GM-HM inequality. And why is that so? Well, notice one thing, and that's a nice construction actually. If you take yourself a this root is actually kind of nice. Lovely. So if you take yourself an nth root, so the geometric mean of reciprocals of this is a crucial part. Yes, those are reciprocals of those. Yeah, so b1 over a1, b2 over a2. This is not a1 over b1, this is b1 over a1 here. That's crucial. Times bn over an is going to be greater than or equal, well, what's going to be greater than or equal to? Well, GM-HM inequality is going to be greater than or equal to the n, yeah, to n over sum of reciprocals of those numbers, and so it's going to be just a1 over b1 plus, well, just stuff an over b. Love. But what is this step right here? Well, I already told you that BIs are just a permutation of AIs, and so those are the same numbers, but just ordered in a different way, in a different order, ordered in a different order. That's nice, yeah. So actually, after multiplying them all together out, you will get the same number as after multiplying all AIs together. Yeah. Because, well, multiplication doesn't care about order, and so we will get the same number in the numerator and the denominator. And so, well, if those in the denominator will be the same, then the whole fraction will be just a 1, and the nth root of 1 is, well, a 1. And so what are we gonna get? Well, we will get that 1 is greater than or equal to n divided by reciprocals from the fractions from under some of the reciprocals of the fractions from under the nth root, which is, well, something like this. But what does it mean? Well, after multiplying both sides of the equation by that sum of the reciprocals, I corrected the dots, yeah? Connected. Yeah, so I've been recording those videos for so long today that I literally find those kinds of things funny. Don't mind me, yeah? And so what we will get is that after multiplying both hand sides by the denominator in this fraction, we will get that the sum of those fractions is greater than or equal to n. But wait! That's literally our thesis, yeah? And so now there's one thing. If we switched BIs with AIs in this thesis right here, it wouldn't really make any difference right here, because, well, this square root would still be a 1. Doesn't really matter, yeah? If you flipped every single one of those fractions right here. And so this is also true for, I mean, a thesis like b1 over a1 plus bn over an would also be greater than or equal to n for any permutation of AIs, which are BIs. And you know, I'm repeating myself, so we will just move on to the next problem. Okay guys, lovely and awesome. We're supposed to prove that a being greater than 1 and not equal to 1 by a being greater than 1 implies that a to the power of n minus 1 is greater than n times a to the n plus 1 power over 2, I mean the power over 2, minus a to the n minus 1 over 2 power. Lovely. We're supposed to prove it for every single n, and yeah, it's gonna be awesome. And it's supposed to be proven for n's, for n's that are natural numbers. I haven't really specified that. Okay, lovely. So now, how do we do this? Well, you could probably try and solve it by induction and stuff like this, but we can, you know, do it 100 times faster using just the AMGM inequality. And so, you know, let's just take this equation right here and rewrite it so we can, pause and ponder. So a to the n minus 1 is greater than n times a to the power of n plus 1 all over 2. Oh, this is supposed to be a plus. And now it looks like South Africa. Nobody cares. Okay, so a to the power of n plus 1 over 2 minus a to the power of n minus 1 all over 2. Beautifully. Man, that's some. I literally just found that my camera died and I was about to. I was about to kill someone. Anyway, so what can we do here? Well, we can just go on and kind of factor out a to the power of n minus 1 from this fraction right here. Yeah, so we will get n times a to the power of n minus 1 over 2. Yeah, and here we will have just the 0, so it will be just 1, and here we will just have n to the 2 over 2, so it will be just a. Yeah, so in the brackets, I mean in the parentheses, we will just get 1 a minus 1. Beautifully. And so what can we do right now? Well, I would opt for something like maybe dividing both sides of the equation by a minus 1, because we have kind of a nice formula for a to the n minus 1 over ai, and that's gonna be actually, because of the formula for the geometric sum, that you, I guess, know, we've proved it in the video induction, looks something like this, yes? So this will be 1 plus a, and we will just add stuff up to a to the n minus 1 power, and it's supposed to be greater than n. Wait, my marker is dying. Okay. Better. Lovely. N just times a to the n minus 1 over 2 power. And you know, I'm thinking, here we have literally just any numbers, yeah? So this is the like 0th power of a, this is the n minus 1 power. So literally those are just n numbers, and here we have n. So if we divided both sides of this equation by n, this would become an arithmetic mean. Lovely, so we could use the AMGM inequality. So let's try and do so. We will have 1 plus a, and we will just add stuff up to n, a to the n minus 1 power, everything divided by n. Oh man, this line is absolutely awesome. Yeah. I wanted to say awful, but awesome sounded even better. Yeah, this one looks terribly, but who cares? So it's supposed to be greater than a to the n minus 1 over 2 power. But now, notice one thing. By the AMGM inequality, this arithmetic mean of those powers of a up to the n minus 1 power is going to be greater or equal to the, well, nth root of the product of 1 times a, and we are just multiplying stuff up to n minus 1 and minus 1 power. And so actually when we're multiplying those a's to powers in terms of n, we will just be adding, you know, this will be just the nth root, yeah, of a to the power of 1 plus, well, 2 plus, and we're adding stuff up to n minus 1. And so by the formula, so you can come up with it if you're a Gauss, or if you're a Gauss, Nobody cares, yeah? So if you are a genius mathematician, you can probably come up with it yourself. This will be just the nth root of, yeah, we actually proved it in the video induction, whatever. So 1 plus n minus 1 times n over 2. This is the formula for the sum of an arithmetic progression. We proved it in the video induction, and this is also a nice like visual proof about like taking arithmetic progression turning it, like kind of upwards, yeah. Dividing, never mind, yeah. So it's gonna be just a to the power of n times n plus n minus 1 plus 1, and then all over 2. There's gonna be just a to the power of n squared over 2, but we're taking the nth root of it. And so this is gonna be equal to just a to the n over 2 power. But as a is greater than 1, if it was, if it could be less than 1, then unfortunately this wasn't the hold. But as a is greater than 1, well then a to the n over 2 power is greater strictly, not greater than or equal to, but greater strictly than a to the n minus 1 over 2, because, well, n over 2 is more than n minus 1 over 2. Lovely. And thus, we've proven this statement. Okay guys, lovely, we can go forward. I checked it. Go forward, we're gonna move forward. We have a, b, and c that are positive real numbers, and we are supposed to prove that 8 cubed by bc plus b cubed by ac plus c cubed by ab is greater than or equal to a plus b plus c. Lovely. So we're supposed to, I would like to do it by AMGM, because it's a video about AMGM. So, how do you do this? Well, I would like you guys to note one thing, because, well, most of the proofs of those kind of a little bit more tricky inequalities involving AMGM, well, just noticing stuff. Well, you can add some magical thing to both sides of the equation, and it's, like magically solves itself. Yeah? So, bear with me. Look at this stuff. We have, for example, a cubed by b times c. And we will add to it ab, and we'll add c. Yeah? So what is this greater than or equal to? I mean, let's take the arithmetic mean of it. And what is greater than or equal to? Well, this is greater than or equal to the cube root of a cubed by b times c times b times c. And so this will be just the a cubed, and this is equal to a. And so this stuff will be literally just, this stuff, a cubed by bc plus b plus c will be greater than or equal to 3 times a. And by the same reasoning, b cubed by ac plus a plus c will be greater than or equal to, well, 3 cube roots of b cubed, which is equal to 3b. And by the same reasoning, once again, c cubed by ab plus a plus b, this a is absolutely awful, yeah? So plus a plus b, not getting any better, a plus b, just a second, bear with me, a plus b is going to be greater than or equal to, what? 3 times c. Beautiful. So now notice, what do we have to actually do to, get this inequality right here to this form? Well, what are we missing? Well, we're missing 2 a's, 2 b's, and 2 c's. So, well, we could, for example, add those c's, b's, and a's on both sides of the equation, but isn't gonna screw up the whole operation here? Well, it's not. Why? Because here we have, we have 1b, 1a, 1c, 1a, 1b, 1c. Yeah. And here we see that this is greater than 3a. This is greater than or equal to than 3b. And this is greater than or equal to than 3c. And so this would be absolutely perfect. Now, let's just add 2 a's, 2 b's, and 2 c's on both sides of the equation, and look what we're gonna get. We will get a cubed by bc plus b plus c. We will get b cubed by ac plus a plus c. And we will get c cubed by ab plus b plus a. And my mark is dying, so pumping. Lovely. But, and we're supposed to prove that it's greater than or equal to 3a plus 3b plus 3c. Can you see it properly? You can, lovely. So, this stuff right here, this is greater than or equal to 3a. This is greater than or equal to 3b. This is greater than or equal to 3c. boom! 3a plus 3b plus 3c is greater than or equal to 3a plus 3b plus 3c, which is true. And so the problem is solved by ING. Okay guys, lovely, we are getting at the last problem of today's video, which is, I didn't really specify it, from the RMO, which is the, well, I guess this is the Indian Mathematical Olympiad, which is absolutely like amazing. I mean, problems from that Olympiad are amazing, I love it. So, in this problem, we're supposed to prove that if A, B, and C are real positive numbers, such that, well, this awfully looking set of fractions is equal to 1, then A times B times C is less than or equal to 1 over 8. Yeah, and so we're gonna be doing this using the AMG inequality. However, you probably already guessed that it is gonna be a lot of expanding, and it's gonna be awful, and it's gonna be painful. But you see, I'm literally all in this yellow dust from markers, and I'm all dirty. So I'm ready to get my hands and hoodie dirty for you guys, and I'm ready to expand some fractions for you guys as well. So let's rewrite it. So we know what we're dealing with here. A over 1 over A, B over 1 over B, and C over 1 over C. We would like to, you know, kind of like probably manipulate this expression in order to get like this A, B, and C, and then maybe something like arithmetic mean or geometric mean will occur somewhere, and we will be able to use some kind of an inequality. Lovely. So first of all, what we have to do is, unfortunately, multiply both sides of the equation by the product of those denominators, which will be absolutely awesome. Absolutely awesome, I want to say. Absolutely awful. Man, so A times 1 plus B times 1 plus C plus B times 1 plus A times 1 plus C, and plus C times 1 plus A times 1 plus B is gonna be equal to, well, 1 plus A, 1 plus C, 1 plus B. Lovely. Well, actually, no, I will multiply at least 2 of them right now. You know what I mean? So, for example, 1 plus A times 1 plus B, this is gonna be 1 plus A plus B plus AB, and we have 1 plus C less, so we're gonna do it in this step. So, okay, lovely, so I'm gonna be multiplying all of those at the same time. So, 1 times 1 is 1, so we will have A, because I'm multiplying also by this A plus, A plus AB, plus AC plus ABC, plus B, plus BA plus BC plus ABC. Okay, lovely, this is the second ABC. Remember that we actually want as many of those ABCs as possible, because, well, if we manage to keep some of them, we will be probably able to get an upper bound of them later using AMGM. Lovely, where was I? Here. C plus CA plus CB plus ABC. What about the right hand side? Well, it's gonna be 1 plus A plus B, everything by 1, so times 1. So 1 plus A plus B plus AB plus C plus CA plus CB plus ABC. Lovely, now it's time to cancel some stuff out from both sides of the equation. This time it's equation. So one of those ABCs is going to die. We're going further. So those A's are going to cancel, those B's are going to cancel, those C's are going to cancel, CA, AB, BA, CB, CB. And well, I kind of killed almost everyone on the right hand side. Apart from the beautiful one here, so lovely, we can leave it there. We got AB plus AC plus BC and plus plus 2 times ABC, beautifully, times 2 times AB and C. And it's equal to A1. Lovely. But now, actually, you know, I would like to do one thing here. Because, well, those are three numbers, yeah, and so maybe it would be nice to use something like the arithmetic geometric mean here. Because if I divided both sides of this equation by a 4, yeah, then I would get 1 over 4 on the right hand side. But this is actually greater than or equal to, well, the root power 4 of the root of a times b times a times c times b times c, abc. So this is literally just 2 times a cubed times b cubed times c cubed. Lovely. And so what we're gonna get is, well, 1 over, and now actually I would like to change this 4 into 2 squared, so I will have 2 squared to the power of 4, so it's going to be 2 to the power of 4 times, no, like 4 times, am I right? Yes, to the power of 8, yeah, lovely. So 2 to the power of 8, yeah, and now I'm going to be and now I have, that is greater than or equal to 2 times a cubed, b cubed, c cubed. Now I can just divide both sides of this equation by 2, so I will get that 1 over 2 to the power of 9 is greater than or equal to a cubed, b cubed, and c cubed. And so this means taking the the cube root of both sides of the inequality this time will yield that 1 over 2 to the power of 3 is greater than or equal to a times b times c, and this is 1 over 8. And so, ladies and gentlemen, this is the end of the solution. Can you see that square? Yeah, you can see the square beautifully, lovely. This brings us to the end of this video. I hope you enjoyed it. If you want more, you probably want more problems, then you can absolutely satisfy your greed on my channel with the like freelance problems I do, like one problem on video and stuff like this, yeah. So anyway, I hope you enjoyed it, and bye.